Okay, hi everybody, my name is Markus. As Alejandro already said, I'm from Germany. I'm working at Codecentric as an IT consultant. Okay, so if we can get the next slide, yes. So we are going to free some things this evening. I guess most of you know about free monads. Can anybody raise his hand if he knows about free applicatives? Okay, I got a few hands. Free monoids? Less hands. Okay. So actually there's a free version of almost every type class that you can imagine. Back again. Okay, so this was the slide, and actually there's a free version of almost any type class. So this talk will explain the technique on how you can derive a free x for whatever x might be. And we will use this technique that I described to apply it to different examples so you can see how we can derive free x. And the takeaway for you, hopefully, is that it's a lot easier than you thought, and you can actually come up with a free version of some type class on your own. The source code is on GitHub. I will already also have a slide with this link at the end again. Okay, so here's one definition of a free functor. So a free functor is just a left adjoint to a forgetful functor. Pretty easy, right? So what's the problem? Okay, so here's another definition. A free thing, let's call it free A, on a type class, A, is itself an A, and a function, let's call it inject, such that for any other thing, B, and a function, let's call it F, that goes from A to B, there has to be a unique homomorphism, whatever that is, G, such that G composed with inject is F. Okay, this is still not really easy, but if you think about the last equation, so on the right-hand side, you have a function that takes an A and returns a B. And the inject takes an A, goes into your free structure, and G then just has to tear it down again and return a B. And this just says that there has to be unique. Okay, this is still complicated, right? So my definition, that is probably not totally correct, so take it with a grain of salt, is a free X, so for example, a free monad, is the minimal structure that satisfies the laws of the type class X. So a free monad has to satisfy all of the laws of a monad, and it has to be the minimal structure. Okay, and then we have this pretty mechanical recipe that I will demonstrate on how we can derive a free X. And this is one, we define the AST. We add the inject clause that we'll see in a moment, write the interpreter, and then we have to check the laws whether it's actually minimal. But before we do that, why would we even want to free something? So one reason is you will get a nice API with your DSL that is based on a type class. So you could use your free monad just like a monad and use flatmap and map, and every Scala developer that uses those functions will be familiar with the DSL. The good thing also is that your program will be reified into a data structure, and you can analyze this data structure, you can optimize it. You can also interpret this program in different ways. So for example, the DSL user never thought about logging, but you can execute the program with some logging added to it. And some disclaimer before we really get into the good stuff. The approach I'm using will be the deep embeddings of the ASLs, or the initial encoding, or the data structure representation. This will not be about finally tackless. This will not really be about optimized free structures. So for example, if you compare the free monad that we will derive to the cats or the Scala Z versions, you will see some differences because they do some optimizations for Scala. We will not really be using free monads. I will just show you how to derive the free monad. But we already saw, I think, enough of free monads already. Some interesting things is that for some type classes, there are multiple different sets of minimal definitions. So for example, for a monad, there are actually 3. So you can not only have flat map and pure, you can also have map, join, and flatten. Join and flatten is the same thing, but there are different ways to have minimal definitions of a monad. And you can apply this technique to all 3 of them, and you will get different free structures that have different characteristics. And the fun thing, yeah, as I said, is that the technique works for all of them, and I always wanted to say that it's a homework for you to do it for the other minimal representations. Okay, so let's free our first X, and let's free the monad first. So here's the monad type class that uses pure and flat map as the minimal set. So pure just lifts a value of type A into our constructor f of A. And the flat map version just takes a monadic value fa and a function that goes from A to a monadic value of B and then just applies this. And the laws for the monad type class are here. So we have left identity, which says when we lift the value using pure and then flat map over it, this should be the same thing as just applying this function without ever calling pure. So this basically says that pure on the left-hand side is not allowed to do any funny stuff. Then we have right identity, which says that if we have a monadic value and we flat map over it with the pure function, then again, pure cannot do any silly stuff. It should be just a monadic value again. So those two laws just require that pure is really as boring as you would think. And the last one is called associativity, and it says that when we have a monadic value and we flat map over it first with f and then with g, this has to be the same thing as doing an inner flat map. So we first call flat map on fa, and then on the inner value we call flat map again. Okay, so let's apply our recipe. So this is the type class again to recall, and let's define our AST. So this is the basic pattern. For each instruction of the type class, we add a case to our ADT. So we have a case class pure that takes a value and just captures it. We have a case class flat map that takes a monadic value and the function and just captures it in the data structure. And then we have our special inject case that just serves to embed our DSL operations into our free monad. Okay, so with this data structure defined, we can already define the monad instance for our free monad. And whenever we call the pure, we just capture the x from here into this data structure. And we do nothing else. For the flat map, we do the same thing again. We just capture it into the data structure and just use the arguments we are provided. And that's it. We are really lazy. And the next step then is we have to provide an interpreter that tears down our free structure into the final one. And for this, we get a target monad M and some natural transformation that just translates our F to our target monad. And then we get a free program. And you don't have to understand this code in detail. It's just about the pattern. We match on our data structure. We go through each case. So if it's pure, we use the monad from the pure from our target monad. If it's an inject, we just use the natural transformation to translate it. And if it's a flat map, we just recursively call the flat map of our target monad and tear down our structure. Okay, so we have our ADT, we have our interpreter. What about the laws? So if we recall the associativity law, we need to satisfy that the subsequent flat maps have to be the same as the inner flat map. And if you apply this to our free monad, you will see that the expression 1 and the expression 2 are not equal. Okay, so this means this is not a free monad, because the free monad has to satisfy the laws. Oh my god. So as a programmer, you could reason that, yeah, but after interpretation, nobody will be allowed to see it. Nobody will be able to see it if the target monad is lawful. So what's the deal? But the mathematician will tell you, no, then it's not a free monad. So the gist of this slide is that there is a spectrum. So you will not always be able to be completely free according to the mathematical definition. But there's a big trade-off that you can already have a lot of functionality even without being totally free, let's call it that. But let's go back to our free monads. So in the previous definition of the monad instance, we said in the flat map case, we just dumply capture it in a data structure. But we can be a little bit smarter and we can use the laws. So we can use a different implementation of flat map and we can match on the monadic value that is passed in. And if it's already a pure node, then we can just eliminate this pure node, because according to a left identity, this has to be the same thing as just applying f to x directly. So we apply the left identity law. With the inject case, we can do nothing smart here. We just do the same thing. And with the flat map case, we can check whether we are flat mapping over a flat map. And according to associativity, we can just transform this into an inner flat map. So we just capture this as a function that then returns an inner flat map node. And again, according to the laws, we didn't change anything about the program. Okay, so what do we learn? Well, the laws are not boring. They allow us to do refactorings in our code day to day, and they also allow us to do optimizations on our structure. And just by adhering to the law, we actually made our free monad more stack safe by accident. Because if you think about evaluation of the first line here, you would have to recurse down into all the flat map nodes and then come up again. And this just screams for stack overflow. But in the second case, after associativity, you can just you can interpret the first flat map nodes FA, and then you can call the function, and then you get back another flat map node, which you can then interpret. So you're basically trading stack for heap here. So we didn't even think about this, but just by adhering to the laws, we got stack safety. Okay, so this is basically the end of the first example. We freed our monads. And what we get is our DSL will have monadic expressiveness. So we can have flat maps, we can have maps. Any Scala programmer will be able to use this. We can have branching, loops, any fancy control flow you can think of, basically. Okay, so after freeing the monad, what else could we free? So how about the functor? So our recipe is just the same again. We define an AST for all of the operations, add our inject case, write the interpreter, and then we check the laws. So here's the type class. We have the functor type class that just has a higher kind of type constructor, and a function map that, given a functorial value and a function, will just apply this function to the value. What are the laws? Well, we have identity, which says that whenever we map over the functorial value with the identity, this does nothing strange. It just leaves the value untouched. And we have the composition law, which says that when we map twice with two different functions, this is the same as just mapping once with the composition of the function. Okay, so let's get started with our AST. We call it our ADT free functor. We have a case for the fmap, which just captures the functorial value, fa, and the function f, and just returns a free functor value again. And we have a second case, which is our added inject case to inject our DSL. Okay, that was pretty easy, just two cases. So the next question we have to ask ourselves is, can we get rid of anything here? And in this case, if you look closely at the inject case and compare it with the fmap case, you can see that both of them capture a functorial value of type fa. So we have fa here and f of x here, but you can just substitute x for a. And then we have only one more additional argument in the fmap case. And if you substitute this with identity, you could just replace inject with fmap. So we can get rid of this case of our ADT and just replace it with a smart constructor that returns an fmap node that applies identity to it. Okay, so can anybody see what's wrong with this code from an OO perspective? Any ideas? So any OO programmer will tell you this is the code smell. Yeah, it's not really about composition and inheritance. It's more like we have an abstract class, but only one subclass. So what's the point of having the superclass at all if you only have one subclass? This is like 00101. And the reason we have this superclass and the subclass is because fmap has an additional type parameter here. So in order to get rid of this superclass, we have to do something about this. And we can solve this by using an abstract type member that just captures our existential type x, because we don't really need it from the outside. We just need it to capture whatever was the functorial value we are mapping over. And then we just can transform our inject smart constructor to instantiate our fmap node, and that just assigns the x to the correct type value. And then if you want to be really cool, we can just name it Coyonida, because that's actually the name for the free functor if you derive it via category theory. But we just came up with it by applying our recipe, which is pretty cool. Okay, so we can define our functor instance as we would do normally. So when you have a functor for Coyonida, which sounds already a lot cooler, then you just, in the case of map, you create a new node that captures the two arguments, same as for the free monad. And the interpreter is actually really, really easy. It's just one line of code. You just use the target functor to map over the Coyonida's functorial value and apply the function. That's basically it. So what you get when you free functors is a DSL with, well, functorial expressiveness. So that means you can just call maps as often as you want to, which is not really convincing, but what you get for free from CoreUnida is map fusion, which is pretty cool. So what's more interesting then is you can combine the free functor, for example, with a free monad, and then you can get map fusion in your free monad, which is pretty cool. The interpreter is pretty boring through, but I think it was still fun to just apply the recipe for functors. Okay, so we freed monads and functors. How about monoids? So here's the monoid type class. We have an empty operation that somehow summons up a value of type A, and we have a combine function that, given two values of type A, returns a single value of type A. And again, we define our AST. We have a case for empty, we have a case for inject, and we have a case for combine. No surprises here. Our empty case just extends a free monoid of nothing, and the combine just captures two values. Simple. What are our laws for the monoid type class? Well, if you combine, so this pipe plus pipe is just an infix operator for the combine operation. If you combine empty and x, it should be just x. On the right-hand side, on the left-hand side, those are the two identities. And combination should be associative. Okay, so let's try to enforce those laws in our monoid structure. And our goal is to have our structure correct by constructions. So nobody should be able to construct an invalid AST with our ADT. And we have to make one arbitrary decision. You will see why in a moment. We have to decide whether we want to associate to the left or to the right completely, because we want to be unique. And I decided to the right, and you will see why. Okay, so how can we enforce this during construction time? We can tag everything that is not a combine operation. So we have the straight not combine, and we tag empty with not combine and inject with not combine. And then we allow on the left-hand side of the combine function only values that are not combine. So we just exclude combine. It's not allowed to play with the others. Okay, so at least we got rid of this one. But we also have to get rid of multiple neutral elements, because we only want to have the minimal number of neutral elements in our structure by construction. And we cannot get rid of it completely, because then you would not be able to write a program that consists just of the empty operation. So we have to limit ourselves to a single element. And the idea is to, again, restrict combine to only have real values on the left side. So instead of having everything instead of combine, we have only real values on the left side. Okay, so we can extract the inject, and we can get rid of the not combine trait, because now on the left-hand side we are only allowing inject cases. So those are our DSL instructions at the end of the day. And if you now look at inject a little bit more closer, then, well, it's just a new type wrapper over A. So let's get rid of inject completely. And we are left with only two cases, the empty case and the combine, which only allows values of type A on the left-hand side and any even empty or combine on the right-hand side. So you can nest those to the right as far as you want. Okay, this might start to look familiar, but let's get to it in a moment. You can think about it in the meantime. Let's first define a monoid instance for our free monoid. And in the empty case, we just capture it as an empty node. And in the combine case, we have to be a little bit smarter, because we have to ensure that on the right-hand side, we only have the combine or the empty, and on the left-hand side, only real values. So we pattern match on the first argument. If it's an empty case, we just return our second argument, because we can get rid of this according to the identity laws. And in the combine case, we just nest it to the right. And this ensures that everything is correct. Okay, so now the question to you guys again, does this look familiar if you rename it? Yeah, it's just simple list. It's exactly list. So that's how we derived that list is a free monoid in Scala. And we didn't even know it before. Okay, so we freed our monoid. So we have a DSL for combining things. You could use it, for example, in data processing to just collect things in parallel. Folds work beautifully for this. You can even use it with Spark. The integration can be in parallel, as I said, because it's associative. Okay, great. Now that we can free basically anything with our technique, what should we free? We just need a new target. And I record that at some point in the past, I stumbled over a blog post by Chris Duque, which used a free Boolean algebra to define an a DSL for event predicates, which was pretty cool. So why not free Boolean algebras? And our recipe again is our AST, then the inject case, we write an interpreter, and then we check the loss. So a Boolean algebra, for those of you who don't know them, is something that has the operations true and false, which return a value that represents true and false, surprise. It has something to negate values, and it has the AND and the OR case operations that just combine two values. And you can define the AST for this and just capture everything in data structures as we did for all of the other cases as well. And there are no surprises here, so in the NOT case you just capture one value of free bool A, and in the AND case you just capture two values. And then we just need an interpreter for this. So again, we have our program of free bool A and some translation from A to B. And we just pattern match on our instructions. For true, we use the target Boolean algebras true. For false, the same. For the inject case, we translate with our given translation function. For the NOT case, we call the target Boolean algebra values NOT and then recurse. And the same for OR and AND. We just recurse down. Okay, so this was basically all that we needed to free Boolean algebras. That was pretty simple, also boilerplatey. So what can we do with our discovered structure? And as a reminder, we can use any Boolean operations. So we can true, false, and, or, and also derived operations like XOR, implies, NAND, NOR, and so on and so forth, whatever you can derive from a Boolean algebra. And instead of an event predicate DSL, I decided to have a DSL that is a predicate over sites, and so over websites. And for this, we have DSL that has the ability to look into some terms of a web page. It can check whether a web page was published or modified after some date. It can look into the text of the web page, and it can look in the URL. And after sneaking in some syntactic sugar behind the scenes, you can just write a predicate like this. So you have a smart constructor called term that creates this term node with a string. And then you can just use the ampersand operator to create AND nodes, the exclamation to create NOT nodes, and the pipe operation to create OR nodes. And this should already read pretty nicely. So we filter out websites that have the term functional programming, and it has to be after January 1st, 2018. And it should not have the term Java or Spring in its text, and in the URL should be up north. Okay, so we just need a representation of websites that we can use to search. So you can, for example, imagine that this is loaded from a database or whatever. And this is just a case class that has some fields like terms, URL, the indexed at date, and the text, which is the complete text of the website, basically. And all of our predicates will be run against collection of these. Okay, but I think before this, let's talk about how we evaluate search predicates. So we get a predicate that is just a free Boolean algebra over our search ADT and a site. And then we pattern match on S in the natural transformation. And when it's a term, we look into the site's terms, and so on and so forth for the rest of the operations. And then we just call run free bool with a predicate and the natural transformation. And you could, for example, filter all sites with our search predicate. Okay, so how does this look in practice? So you can define, I hope this is big enough. Maybe let's, this is still at the bottom. I hope you can see it anyway. So we can define some predicate that has some term in it foo. And this would be a valid predicate in our DSL. And then we can arbitrarily combine this, for example, with the AND operation and say that it has to be term foo, and in the URL has to be Google. And we can further combine this with for example, with in text, there should be a bar, and so on and so forth. And we could really write complicated predicates that just use Boolean logic. Like, for example, the one on the slide here. So this one, if you use this in the DSL, as it's written here, you get something back that is just an AST of all of those nodes. And then I have some sites here. Well, I don't know why this is not working anymore. Okay, so I have the sites.up north, which is just an instantiation of the case class, which has some terms like FP conference Toronto up north. It has the URL scala-upnorth.com, and it was indexed at the 29th of September 2018. And the body is just a string body. So we can now do eval search. I think I have to look this up. It's hard without tab completion. Let's copy this. So we can just call eval search with our search predicate from the slide previously and just run it against this site, and it will be true. And if we call eval search with our previous search predicate against a Spring website, it will be false. So we just interpret our Boolean algebra with our DSL. Okay. So this is how you could write a DSL with Boolean expressiveness. But actually, there's way more that you can do with this now that we've freed Boolean algebras. For example, you can perform short-circuiting or other optimizations with the program once you have it, because and false and something else will always be false. And another question is, what can you do if you don't have all of the information? And we will get to this in a moment. And then you can actually partially evaluate your program. So instead of running it to a value like true or false, you can just reduce the AST into something that either is true or false, or some remainder program, and then continue with this remainder program once you have more information. And you can also have a core language versus an extension. So you can have an even richer DSL that is based on some simple DSL, and then you can just translate those layers down into more simple ones. So for example, instead of having just terms and in URL and in text, you could have some combinations or some layers and just provide an even richer DSL to your users, which then de-sugar into your normal language, and it's just nicer for higher level users. And this is also demonstrated in the blog post by Chris Duccio, so if you want to know more about this, you can look there. But we will first look into partial evaluation. And for this, I first wanted to introduce the optimizer. So as I said, you can easily optimize Boolean algebra programs. So for example, if you have double negation here, you can just get rid of the double negation. If you have an OR node and there's true on the left-hand side or the right-hand side, you can just short-circuit everything to true. If there's no AND with a false node on the left or right-hand side, you can just short-circuit everything on to false. Okay, so the idea of the partial evaluation is that you might have not all of the information required to run your predicate to get true or false. But you still want to evaluate as much as possible, and then maybe you send it predicate on or get additional data from somewhere else. In the optimal case, you can already reduce it to true and false in most of the cases. Then you can just forget about loading the additional information. So we define for this a partial evaluator that takes a program P of free bool A and a function that tries to evaluate from A to an option of B if it's possible, where B is our Boolean algebra type, and it returns in either of a remaining program or the target Boolean algebra. So it could be, for example, true or false if you use Boolean as the instance for your Boolean algebra. And for this we just pattern match. If our program is already a true, we return a right of the target algebra as true. So it could be just write true. For the inject case, we use our normal our f, which returns an option, and we'll see in a moment what this is in our search example. And in the OR case, we would just recurse down the nodes. And we do this for all of the cases. Okay, so let's imagine instead of having sites, we also have a case class site metadata, which has all of the fields of the site, but it's lacking the body because the body might be really big, or it might be, or maybe we have to parse it. So we want to avoid loading the body if possible. And then we define a function partially, which has some site metadata and our search predicate, and just reduces one step of this. So if we have a search predicate that checks the term, we can do this. We return a sum of the check whether it contains the T. And for the after, we can do it as well. For the in URL, we can also do it, but not for in-text. For in-text, we return none because we can do this on sites metadata. We need the whole website for this. Okay, so what we can do now is we use the same predicate as before, but we can run our predicate against only a site metadata. And if we run our search predicate called search against the up north site, we will get back, where is it, left of a remaining program, which is just a knot of in-text Spring. So if you recall our search predicate, it checks whether in the text there is not Java and not Spring. And in this case, it was just, it reduced everything to just checking whether in the text is Spring. Okay, and if we run this again, the other website's metadata, which might be a Spring website, then we get back a right or false, because it was already able to check whether this website contains Java or Spring in the terms, I guess, or something like there, and it was already able to short-circuit everything into false. So for this website, we don't even have to load the text. We just already have our answer. For the up north website, we would have to check whether in the text there is not the text Spring. Okay, so in this case, we would probably serialize everything and send it on to another microservice, or maybe we could just load it from the database, whatever. Okay, so with this, we freed Boolean algebras, which I think is a good example of an underused structure. We demonstrated how to do partial evaluation on this structure that you can freely inspect, optimize, and interpret. You could, for example, serialize the AST because there are no functions, so you could serialize it to JSON or protobuf or Avro and send it over the wire, which you cannot do with free monads. And as an exercise, you can try to minimize the AST representation according to the laws. But spoiler, this is not really easy because there are a lot of laws, and finding a minimal canonical structure is not as easy as you might think in this case. But as I said, it's still free enough for our purpose, because as long as the target Boolean algebra is lawful, nobody will notice anyway. Okay, here are some resources. The blog post I referenced is the one from Christukio there. The source code will be on my GitHub. You can find the source code for the slides and all of the code examples there. And with that, I hope you can go forth and free all the things. Thank you. Any questions? I know it's late. Yes?
Have you ever serialized them and whatnot in practice?
I did not for production, but I did for fun, yeah. So the answer was whether I ever serialized them, and I did only for fun. But only JSON. Any other questions? Yes?
It's not a question. I just wanted to thank you for the full text search example. That actually seems like a pretty practical. You could imagine that would be very expensive to use one.
So it was more note that it was a thanks for the full text search example. So you can see why it's actually useful. Okay, then thank you again.